I'm Geoff Notkin, science writer, meteorite specialist, half of television's Meteorite Men, and Chief Executive Officer of Aerolite Meteorites Incorporated, a world leader in meteorite recovery, research, and education. Meteorites are pieces of stone or metal or a mixture of both that have fallen to our planet Earth from space, and they're my passion. For the last 25 years, I've traveled all over planet Earth in search of them, and I found thousands, from tiny to giant. I'm standing on the African continent in the mighty Sahara Desert, and I'm here because this is one of the best places on Earth to find meteorites. Why? Well, look around you. It is a wide open, mostly barren space with very few plants. But the real key here is age of surface and dryness. Meteorites, by and large, are very rich in iron. So if they fall in a moist environment like London, England, where I grew up, they're going to decay quickly and fall apart. If they land in a dry, warm environment like the Sahara Desert, they're going to be preserved for a much longer period of time. And if they fall on an ancient surface like this desert plain, they will stay there perhaps for thousands of years or even tens of thousands of years until somebody like me sees them and picks them up and studies them for science. I'm going to teach you exactly how to recognize a meteorite and how to distinguish them from ordinary terrestrial rocks. Because if you want to find meteorites, the first step in your journey is understanding exactly what they look like. There's absolutely no better way to learn and understand meteorite identification than looking at meteorites and earth rocks in the field where they were found. These are all things that have been found recently out here on our expedition, all on this surface and pretty close to this area. And I'm going to teach you how to distinguish the meteorite from the meteorong. Almost all meteorites are rich in iron, and the most abundant meteorite type is the ordinary chondrite. Now, I don't think there's anything ordinary about chondrites, but that's their scientific name. And when we look for meteorites, we look for dark, heavy rocks that seem out of place in the environment. Chondrites are rich in iron, so they're going to stick to a magnet. And this is a very powerful rare earth magnet, actually two stuck together for extra power. So here's our first candidate. Does it stick to a magnet? No. This is a very ordinary earth rock. It's a little bit shiny. It has an interesting shape that is quite reminiscent of some meteorites. And when most meteorites hurtle through the atmosphere, their surfaces ablate, they melt, they get changed into a different shape. And while this shape is somewhat reminiscent of what we might call an oriented meteorite with that rounded, ablated shape, it doesn't stick to a magnet, it's not the real thing. And almost all meteorites that we find on Earth are chondrites and will contain metal. So if they don't stick to a magnet, we tend to discard them as possible meteorites. Here's a dark, reddish-brown, rounded rock, really stood out on this light-colored desert floor. This is the type of color that we're looking for. Meteorites acquire a fusion crust, a dark, burned rind, as they hurtle through the atmosphere. And when they've been lying in the desert for a few hundred or thousand years, that fusion crust begins to oxidize and turns a kind of reddish brown. So the shape is good, the color is quite good, but there's no magnetic attraction. There's no iron in that rock. This one's really intriguing. This was lying on the surface right over there. It looks very melted here, as if this surface has been burned and flowed, and there's a strange indentation here that might be mistaken for a miniature crater and impact pit. It's an optical illusion. This is not fusion crust. This is a varnish that's been acquired by a long sojourn in the desert, and this is actually wind sculpting. They're not melt lines. Again, no magnetic attraction. What about this interesting thing? Well, not only is it not a meteorite, it's not even natural. This is an Acheulean hand axe that I found on the first day of the expedition, lying on the surface just like this. A beautiful ancient tool from long vanished people. So a wonderful find, and definitely a keeper. That's going home with me. But wrong color, it's a little bit too brown, no magnetic attraction. Something else that's found in some abundance out here on the flats in the Sahara, ancient human-made pottery. So wrong color, we don't see yellow and orange meteorites, no attraction to the magnet. This one really stood out. I saw this from probably 50 feet away. Look at the dark surface, it's a little bit shiny. It doesn't look like any of the other rocks in the area. So I bent over, picked it up, and when I looked at it very closely, I discovered that it's packed with fossils. This is actually a conglomeration of ancient brachiopods, little tiny bivalve shells packed together. So that's also going home with me. So another nice find, but not a meteorite. This thing, definitely not. Although it's got kind of a rounded shape, this is very light in color and it's light in weight. This is just an ordinary terrestrial rock, nothing interesting. We're looking for dark, heavy rocks that attract to a magnet, and this is not one of them. This kind of material is sent to me all the time by hopefuls who think they found a meteorite. You see the holes in it? Those are called vesicles, and those are caused when gas escapes from a molten rock. So this is a type of volcanic rock that was once in a liquid state, and as it cooled and the air escaped, it made those holes. And we never see large vesicles like this in a meteorite. Rather than falling to Earth from outer space, it bubbled up onto the surface from the inside of the Earth. So discard anything that shows vesicles, although you might want to keep this piece if you found it, because this is also an artifact. This rounded face here shows that it was once part of a pestle and mortar that was used for grinding grain or other materials. Again, no magnetic attraction. But this is really key in meteorite identification because a lot of dense, dark rocks are volcanic in origin. And if you see these pinprick holes, vesicles, you do not have a meteorite. Now this one's really promising. We're looking for dark reddish-brown rocks that attract to a magnet, have an interesting shape. This almost looks like it ablated in the atmosphere, but actually this is a ventifact. This is a terrestrial rock that has been sculpted and shaped by wind-blown sand. So over thousands of years, this is sat out here on the desert floor, and the wind, of which we've seen a lot on this expedition, has blown sand against the faces, polishing it and giving it a nice shiny exterior. So it sure looks like a meteorite, but no magnetic attraction. Can you guess that I saved the best for last? This is the real thing. This is a Sahara stone meteorite, an ordinary chondrite. Look at that beautiful bronze, brown, black color. It's just slightly different, a little darker and a little shinier than every other rock out here, but this is the clincher. A powerful magnet sticks very strongly to this because it's about 20% iron. And here's another telltale clue. Look at the sculpted shape. It's almost like someone's polished this. And that's because as it flew through the atmosphere, the surface ablated and it formed these little indentations called regmaglyphs. And this is denser by far than all these other rocks. So it's very heavy for its size. The color is key. The shape is key. The little indentations, the weathered fusion crust that's got that brown, bronzy color and that super nice attraction to a magnet. When you're out meteorite hunting, that's the click sound that you want to hear. Now, not every rock that adheres to a magnet is a meteorite, but it's definitely a step in the right direction. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15 specimens. Only one of them was the real thing. That is a genuine visitor from outer space, a Sahara stone meteorite. Let me tell you, that Sahara expedition was some trip. That was a venture that my friend, hunting partner, and Meteorite Men co-host Steve Arnold and I organized as part of our Meteorite Adventures meteorite hunting expeditions. And I'll tell you more about that later. When I got back to the States after the big Sahara adventure, I thought, well, I'll go to my doctor for a checkup just to be sure because, you know, hostile circumstances. Who knows what you might encounter out there in the deep Sahara, riding camels and such. And she took one look at me and said, what happened to your back? It's fine now. But I said, well, I was in a vintage Land Rover with no suspension, traveling across the Sahara for many days. And the experience was a bit like putting a bean in a can and shaking it vigorously. And then, of course, there were the camels and the hiking over the sand dunes and the digging and the rest of it. And maybe in a future video, if you're good and write in with requests, we will talk about meteorite hunting from camelback. But I'll save that for the future so you have something to look forward to. Now, it's one thing to look at rocks that you found in the field. It's distracting, there's sun, there's flies, there's sandstorms, whatever. And it is another thing entirely to study them in the laboratory. So you will be very pleased to know that I brought some of those finds back from the Sahara, and we are going to take a closer look at them here in the lab and really become familiar with some of their distinguishing features. Much as I might like to, I don't bring back every rock that I find on an expedition, because if I did, my house would look like the Grand Canyon by now. So I was good, and I just returned from the Sahara with the highlights of my finds. Obviously the meteorites, and obviously the prehistoric axe handles. But I didn't bother bringing back all the meteowrongs. Now, perhaps the single most important tool in the toolkit of the meteorite hunter, and an indispensable item for meteorite identification, as you already know, is the magnet. This is no ordinary hardware store magnet. This is a powerful, excellent, professional, and potentially dangerous rare earth magnet. This has a 30-pound pull. It's lightweight, it's very powerful, and this is the exact magnet that I use in the field. If you've watched Meteorite Men, you've seen me dig a lot of holes searching for suspected meteorites with one or more of these stuck to my rock hammer. Why do we use the magnet? Because almost all meteorites contain iron. And that is typically our very first step in identifying a potential meteorite. Let's have a closer look at some of these finds from the Sahara. Well, here is the beautiful ancient axe head. This was actually one of the first things that I found on the expedition. And the color and the shape are very, very close to what I'd expect from a stone meteorite. Look at the rounded surface. It's shiny, it's dark, it's got that sort of brownish, reddish tint. It even has a flat side and a rounded side, which is a characteristic that we see in some oriented meteorites. But absolutely no attraction to the magnet. And if you look more closely, you will see that it has grooves, markings, where the surface of this was chipped by an ancient toolmaker. So it's not a meteorite, but it is a fantastic find. One of my favorite recoveries in recent years. Next up, well, I had to bring this one home because it's a rock that's just packed full of fossils. These are marine fossils, and it doesn't really have the surface features that I'd expect to see in a meteorite, but it was a dark rock. It was a little out of place. It looked different from the others. Zero attraction to the magnet. Well, these don't look remotely like meteorites, but they are ancient pottery pieces, and who can resist when you see them lying on the desert floor? Again, no attraction to the magnet. But then what is this interesting piece at the end of the queue? Well, this is the real meteorite. This is a chondrite, a stony meteorite. Look at the dark surface. It's shiny. It's got
a rounded aspect to it, caused when it hurtled through the atmosphere and some of its surface ablated. It has little indentations called thumbprints, and you will not be a bit surprised to discover that it passes the magnet test very, very, very well. And what is remarkable is this rock probably only contains about 20% iron. And that is why we use the rare earth magnet, because I promise you, a refrigerator magnet or a toy magnet that you might have lying around the house somewhere is not going to work with meteorite testing. So there it is, a whole individual that is a complete stone that didn't break during flight or at some subsequent time during its long sojourn on Earth. This is the real deal. Now you've met a stone meteorite. And stones are one of the three main types of meteorites. In fact, they're the most abundant. They're still extremely rare, but there are more stone meteorites than other types. And I'm going to show you the surface characteristics and features that we expect to see in all of the three main groups. But before we do that, I've got something else really important to show you. I want you to meet a couple of meteowrongs. Meteorite, meteorong. I know it's a bit of a silly joke, but we just never get tired of it. These are rocks that do not come from space, and yet these are two of the types that are most frequently mistaken for meteorites. Let's take a closer look at their features. This one is lava, igneous rock that was once molten and was probably thrown out of a volcano. If you think back to the segment that we filmed in the Sahara, you will already know why this is not a meteorite, because it is full of vesicles, holes that were caused as gas escaped while it cooled from a molten state, and zero attraction to the magnet. Now, let's take a close look at the undisputed king of the rascals of the meteorong world, and this is slag. There is no thing that is mistaken for meteorites more frequently than this. Why? Well, it looks like it was melted, which it was. It has a kind of a metallic look to it. It's quite dense, and it's got that reddish-brown color that we often see in meteorites. Most infuriating of all, it attracts to the magnet. But it's not a meteorite. And how do we know that? Well, as I hope you will have discovered by now, we can discount this because it has vesicles on one face. We do not find vesicles in meteorites. I say it again for emphasis. And here's something a little bit more unique to slag. It attracts with different amounts of, you might say, enthusiasm on different faces. The magnet adheres very well on this face, not so well on this face. And that doesn't happen with meteorites, because by and large, meteorites have a uniform consistency throughout. So what is this? And how is it that slag is often found in the weirdest, most inaccessible places, which supports the incorrect theory that it might have fallen from space? Well, slag is the byproduct of smelting, which is often a byproduct of prospecting for rare metals. So those in search of gold and silver and other valuable items have ranged over most of the surface of the planet at some point in history, extracting ores from veins, melting it down to test the quality. And this is what's left behind from a little portable smelter. And let me tell you, prospectors have been everywhere. So just because you find a strange rock in a strange place doesn't mean it's a meteorite. So lava, vesicles, no attraction to the magnet. Slag, vesicles, strange attraction to the magnet, which varies on different faces. Neither of them are meteorites. Now that we've looked at the features of common meteowrongs, I want to go back to the real thing. As I mentioned earlier, there are three main groups of meteorites: the stones, the irons, and the stony irons. And the one from the Sahara that we looked at in detail, which is right here, is a stone. And we're going to look at some other examples of stone meteorites that show definitive features you should look for. If you decide to go meteorite hunting and you're out in the field, this is the most likely type of meteorite that you're going to find. It's called an ordinary chondrite. These come to us from asteroids within the asteroid belt between Mars and Jupiter, and they were once part of the crust or mantle of those asteroids. Now, as I mentioned earlier, almost all meteorites contain iron, and I'm going to demonstrate that again with our rare earth magnet. It adheres quite well to this stone meteorite that was found here in the States, and it has a uniform attraction all over the meteorite surface because the composition of most meteorites is uniform throughout. This exhibits most of the features that we would expect to find in a meteorite. It is dark because its surface burned, forming fusion crust, and because this is a meteorite that's been on the Earth's surface for a long time, that fusion crust has begun to weather and oxidize. And so what was once a rich black has now been terrestrialized to a reddish ochre brown. It's heavy for its weight because it's about 20% iron. It has a somewhat shiny surface. And again, it has those little indentations called regmaglypts that we frequently see on the surface of whole meteorites because it was their surface that altered during flight, forming those little indentations. I mentioned that meteorites acquire fusion crust when they hurtle through the atmosphere, and that's because their surface becomes superheated and actually burns. And when you find a freshly fallen meteorite that's only been on the Earth for a short period of time, that fusion crust can be as black as the surface of a charcoal briquette. And nothing demonstrates that better than these beautiful Buzzard Coulee stone meteorites that I found on a thrilling expedition to Saskatchewan in Canada. I went with one of my hunting colleagues shortly after the fall, and we found hundreds of meteorites during a relatively short period of time. They'd only been on the ground for a few months, and the finds demonstrate that you can recover meteorites of varying size in quite a small area. I found all four of these and many others over a 2-day period. Now notice the rich black crust on these. This is not something that you see in terrestrial rocks. So if you're searching for meteorites that have fallen very recently on Earth, you can expect them to look like this. But this fusion crust is fragile, it's delicate, and it decays quickly over time. And that phenomenon is extremely well demonstrated by these Ash Creek stones that I found in Texas. Now, these hold a special appeal to me because they were a personal record for me in the shortest period of time that had elapsed between a witnessed fall, a fireball that was seen over Texas, and me actually finding them on the surface, which was only a few days. So I picked these up in a cotton field in rural Texas, and they've got perfect black fusion crust. And then I went back to the site about a year later when we were filming an episode of Meteorite Men and found this one, a larger one, in the same area. And look at the difference that 1 year on Earth makes in a relatively dry environment such as Texas. So even meteorites that have been on the Earth for a relatively short period of time in a relatively dry environment will still begin to oxidize and change because of their exposure to Earth's moist atmosphere. I hope that by now you're becoming familiar with the surface characteristics we expect to see in meteorites that have been on the Earth for a long period of time, and meteorites that I picked up very shortly after they were part of a witnessed fireable event. But it's really important to understand the internal structure of meteorites as well, especially when you're looking at stones, because many Earth rocks over time can take on superficial surface characteristics that seem to resemble meteorites. And so even though I've been doing this for decades and I've found thousands of meteorites on 6 continents, I still sometimes need to take them to the lab for a more detailed examination. And regardless, when I find a new meteorite, I want to remove a piece and donate it to our colleagues in academia so that they can perform a legitimate classification process on it, see if there is any important scientific information to be gained from this new find, and also assign it an official name which will go into the permanent literature of all of meteorite history and science. In order to do that, we need to remove a piece both for study and for donation to the university or lab that we're working with. This is a fairly recent find, also, interestingly enough, from the hot deserts of Northwest Africa. This was found on the edge of the Sahara. We could tell that it was a meteorite. It had a uniform attraction to the magnet, had surface characteristics that we would expect to see, that we've already discussed. But we wanted to know more, so a piece was removed in the lab with a special saw, and it was sent to one of our university colleagues for identification and classification. And if you look carefully at the inside of this meteorite, and let me say this is just a rough cut, this has not been polished or otherwise prepared in the lab, this is the face just as the saw left it. Even though it's a basic cut, if you look carefully, you will see that it is full of chondrules. And chondrules are a definitive indicator for stone meteorites. We do not ever see chondrules in any Earth rock. They are absolutely unique to space rocks, and they constitute the most abundant group of meteorites, the chondrites. So chondrites take their name from the chondrules that they contain, and chondrules were formed at the very beginning of our solar system in the solar disk, and they are tiny, tiny glassy spheres. Since this meteorite is currently undergoing the classification process, we're not going to do anything else with it until we get the results. And the piece that was removed carefully in the lab that went to our colleagues in academia for classification and analysis will remain permanently with them as a donation from Aerolite Meteorites to their research collection. And it will stay permanently in that research collection, and it will always be known as the type specimen. That is the first analyzed, classified example of a new meteorite find. And it's always a thrill and a pleasure for us to be able to contribute an example of a new meteorite to our colleagues in academia. Once we get the results back, we'll decide what to do with that. Will we make additional slices? Will we donate other pieces? Will we keep it whole as a potential museum exhibit? That will be determined by the outcome of the classification analysis. For now, I want to show you what chondrules look like when they've really been prepared perfectly and beautifully in the lab. This is another chondrule-rich meteorite that was found in Northwest Africa. And I've hardly ever seen a stone meteorite that shows off its chondrules as beautifully as this. Notice how they vary in size and color and are very densely packed. All chondrite meteorites contain evidence of chondrules, but they surely don't all look like this. I picked this because it's one of my favorites, and it shows amazing preservation of the chondrules and also a great abundance of size and color and density. But I'm going to show you how very different chondrules appear in other types of chondrite meteorites. This is the Gold Basin meteorite from my adopted home state of Arizona. And this meteorite was discovered by my late friend Jim Cree, who was a gold prospector turned meteorite hunter after he accidentally discovered an enormous strewn field in northwest Arizona while he was out looking for gold nuggets. It's another nice example of what an older meteorite looks like. I found this piece partially buried. You can see a difference in the surface color. This is the part that was exposed and it was weathered by the elements. And this is the part that was buried and began to attract some caliche on its submerged face. And when Gold Basin is cut and polished in the lab, it also displays evidence of chondrules, but that evidence is very different from the first piece that we looked at. While the Gold Basin meteorite clearly displays chondrules, they're not as abundant or as colorful or as densely packed as the chondrules that we see in the first example, a meteorite known as Northwest Africa 4502. And now I'm going to show you another variance in chondrules. And this is a meteorite for which I have a lot of affection. It's called Coffeyville, and it was found in Kansas by a landowner, and it's one of those great find stories, one of the find stories that you might aspire to yourself, and it shows the value of understanding the features of meteorites. The finder was the landowner, and he was out walking around on his property when he noticed a large, unusual-looking rock sticking partially out of the ground. He tested it with a magnet. It adhered well. It was dark, rusty, red, and when he pulled it out of the ground, it seemed very heavy. So he got in touch with me, described the find circumstances. I said, sounds pretty promising. Cut off a small piece, sent it to me for analysis, and we immediately saw evidence of chondrules within it, as well as nickel, iron, metal flakes, which we will get to in a moment. The point I'm making here is that all three of these meteorites, Northwest Africa 4502, Gold Basin, and Coffeyville, are all chondrites, yet their internal visual characteristics vary tremendously. By understanding how chondrules change in different types of chondrites, you will help yourself make the journey to becoming an expert in meteorite identification. And the key here is these chondrules were altered on their parent body before they ever made it to Earth. And the parent body is the origin point for meteorites. In the case of these three examples, all asteroids. And those asteroids had different life stories. On some of them, heat and pressure were generated. There may have been water present. There may have even been geological activities, which resulted in the chondrules becoming melted or otherwise deformed over time. So in some meteorites, like 4502, we see perfect, pristine chondrules. In some, like Gold Basin, we see chondrules that have deteriorated somewhat over the multi-million year history of those asteroids. And in Coffeyville, we see very little evidence of chondrules because the asteroid from which this meteorite originated went through massive changes during its life history. You're now familiar with the surface characteristics we expect to see in meteorites that have been on the Earth for a long period of time, on meteorites that have fallen to Earth recently, and you have become familiar with chondrules and what they look like. But there's another very important characteristic that the vast majority of stone meteorites exhibit, and that is an abundance of small nickel iron flecks suspended within the matrix. And the presence of these little nickel iron inclusions explains why even stone meteorites adhere well to a magnet. One of the tests that we do, in addition to looking for chondrules, is to grind off a small corner of a suspected meteorite or remove a face in the lab and then look for the presence of these shiny nickel iron pieces that almost look like stars in the night sky. I started with stone meteorites because they're the largest of the three main groups. They're also probably the most difficult to identify in the field. But don't be discouraged. Now we're going to move on to iron meteorites, my favorite. And they're a whole lot easier to recognize in the field and in the lab. There isn't much on this planet, or other planets, in fact, that I find more fascinating than my favorite subject, iron meteorites. What are they? Well, they've had a pretty fascinating life story. We are looking at something that was once part of the molten core of a massive asteroid that lived way out there in deep space, somewhere between Mars and Jupiter, about 250 million miles from us. And it takes a large celestial body to have sufficient mass to generate a core that is made of molten material. At some point in the distant past, probably as a result of collision between two asteroids, some of that material was blasted off into space, cooling slowly, and some of it landed here on Earth. There are many different scientific subgroups of iron meteorites, but of particular interest to the meteorite hunter or collector, or those of you who wish to learn meteorite identification, is this fact. We see iron meteorites here on Earth in two different forms: the way they are found, the way they fall. It's not a scientific classification, rather it's a function of their catastrophic journey through Earth's atmosphere and eventual collision with the surface of our planet. The two types are individuals and shrapnel. And an individual, like this beautiful piece, traveled through the atmosphere as an autonomous mass and landed as a whole piece. And we can tell it's an individual because its entire surface is covered by those little indentations that we saw in the stone meteorites called regmaglyphs or thumbprints. And these are a result of surface melting when the incoming mass was heated to such a high temperature that its surface actually flowed and acquired these remarkable little surface features. We have here an example of the Campo del Cielo iron meteorite, one of the oldest known meteorites on planet Earth, and it was first discovered in 1576 in South America by the Spanish. They must have been somewhat perplexed to see these large and strangely shaped pieces of iron lying around on the surface. It wasn't until hundreds of years later that they were positively identified as meteorite fragments. This is a whole individual. Look at the beautiful surface features, indentations, remarkable sculptural aspect, and oh my gosh, this is dense. This is about 93% iron and 7% nickel with a few trace elements. And does it attract to a magnet? Does it ever? It attracts so strongly to one of our rare earth magnets that you can hardly pull it off. So in the field, not only do we use strong magnets to aid in meteorite identification, but we also use them to aid in meteorite recovery, as it can be quite difficult to precisely locate a buried target in the earth. And if you've watched Meteorite Men, you've seen me with my rock hammer with magnets attached to it, digging around in the loose soil after an excavation, trying to get that suspected iron meteorite to jump onto the magnet. So here I have 2 iron meteorites in as-found condition, and I want you to appreciate both the similarities and the differences. Campo del Cielo landed on Earth about 5,600 years ago, and as mentioned, was first discovered in 1576. So it's been experiencing Earth's moist, oxygen-rich atmosphere for thousands of years, and that has caused the surface to oxidize and degrade somewhat, although you can still very clearly see the regmaglit indentations on its surface. This beautiful piece is Sikhote Alin, the Russian iron that was seen to fall in eastern Siberia in 1947. So this one's been on the Earth for thousands of years. This one's been on the Earth for decades. And they show a marked difference in their degree of preservation. If you were out looking for iron meteorites, it is fairly unlikely that you will find a recent fall because there haven't been many. So most recovered iron meteorites look more like this. They have a heavily oxidized surface, and they show those distinctive characteristics. Notice not just the thumbprint indentations, the sculptural aspect, but also the color. It has that bronze, orange, ochre color that we associate with meteorites that have been on planet Earth for a while. Here, I have an example of a similar iron meteorite that's been cleaned. Now, if you see meteorites in an auction catalog or for sale on a website, they more typically look like this, but it's very unusual that you would find a meteorite in the field that looks like this. This has been lightly cleaned with a wire brush to remove the oxidation. It still very clearly displays the regmaglit indentations, but the telltale oxidized patina has been removed. Important distinction to remember. This is what meteorites typically look like in the marketplace, and this is what they typically look like in the field. So these landed on their own, some of them in the distant past, some of them quite recently, and these exploded either during flight or upon impact or both. Shrapnel is fascinating because shrapnel specimens really demonstrate the fury that a meteorite experiences during its journey to Earth. And we call them shrapnel because of their similarity to the twisted remains of bombs and artillery shells that have been used in military conflict. And they have sometimes been mistaken for just that because of their angular shard-like appearance. These are pieces that I found on expeditions of mine. This is Henbury from the Australian outback. This is Whitecourt from Alberta in Canada. These are both crater-forming irons. And that means they were large enough, massive enough, and traveling at sufficient velocity to punch right through Earth's atmosphere and hit the surface of our planet with such fervor that they caused a tremendous explosion that formed a crater in the ground. When that happens, the meteorite itself is ripped into shard-like fragments, which show the features associated with shrapnel. Notice the torn, very sharp edges. You could cut leather or paper with the points on this. So these two are exactly as they came out of the ground, and they teach us a very valuable lesson, which is buried meteorites, particularly irons, tend to take on some of the characteristics of the environment in which they're found. So the Australian desert is very rich in iron, And if you've seen photographs of the outback, it's typically very red. And so iron meteorites that have been lying in that environment for thousands of years themselves become red and become similar to the colors that we see in the landscape. The Whitecourt crater in northern Alberta in Canada is as different as could be from Henbury. The Henbury craters are thousands of years old. There are 15 of them in close proximity. There's only one Whitecourt crater, and it has a very young geologic age, only 1,100 years, making it one of the youngest true craters on Earth. And it's also in soil, which is very unusual. Soil is a landform that will decay and erode quickly in geologic time spans. So within a few thousand years, we might expect that crater to have disappeared completely. But the important lesson for the meteorite identification is that this meteorite is brown because it's been sitting in dirt for 1,100 years. So oxidized iron shrapnel from the iron-rich deserts of Central Australia and brown, weathered Whitecourt specimen from the rich soils of northern Canada. In much the same way that most stone meteorites, the chondrites, exhibit a remarkable feature that we don't see in earth rocks, so do iron meteorites. And the internal feature that is unique to irons is known as the Widmanstätten pattern. And this is a beautiful, geometric, lattice-like structure that is made up of two different nickel-iron alloys. Now, you may be surprised to know that iron is actually a crystal, but on Earth, we rarely see its crystalline form. However, in space, as the once molten cores of these asteroids cooled, they did so very, very slowly over millions of years. And that allowed this crystalline form to really take shape. And if you cut a meteorite, an iron meteorite, in the lab and properly prepare its surface, you will discover that in most cases, it reveals this marvelous pattern named after a German researcher, Count von Widmanstätten, who described it. The Widmanstätten pattern is one of the definitive tests for meteorites, and it needs to be carried out in the lab. We do not see this pattern in any earth rocks. So if we have a suspected iron meteorite and we want to verify, that is one of the best ways in which we can do it. And here's the most interesting fact about the Widmanstätten pattern. Not only is this feature unique to iron meteorites, and to a lesser degree in stony iron meteorites, every iron meteorite has a different pattern. So in that sense, they're a bit like cosmic snowflakes, but they're a lot heavier. The third and final main group of meteorites is the rarest and also the most intriguing. Please meet the mysterious and beautiful stony iron meteorites, divided into two subgroups, the mesositerites and the pallasites. Now, in the earlier days of meteorite science, it was thought that the mesositerites and the pallasites formed in similar ways, which is why they were joined together into the stony iron group. We now believe that is not the case, and their life stories are different and also very enthralling. Mesositerites are, like their cousins, the pallasites, about 50% nickel iron and 50% silicate or stony material. In other words, they're halfway between the irons and the stones. They attract strongly to a magnet. They show fascinating and unique features on the interior. But the way in which they got here is perhaps the most fascinating of all. It's believed that mesositerites formed when two different types of asteroids collided with each other. One of the asteroids may have been of a stony type, and the other may have had a molten core. And it's thought that this process of collision injected the material from one asteroid into the other, creating this extraordinary mixture of stony silicate material and nickel iron. And if you look carefully at this prepared face of a mesosiderite, you will immediately see that it doesn't look like anything else on Earth. This is really a mysterious and alluring space rock. Many enthusiasts and collectors think that pallasites are the most beautiful meteorite of all, and it's easy to understand why. Like their cousins, the mesosiderites, they're made up of roughly half iron and half silicate material, but in this case, the silicate material is the mineral olivine, and in the gemstone world, olivine is known as peridot. So when you take a pallasite, prepare it in the lab, and look at its interior, you see a wealth of extraterrestrial gemstones suspended in a shiny nickel iron matrix. These crystals are very easy to see when you have a prepared face, but they're also quite easily distinguishable on the surface if you know what to look for, and that can be a key factor in identifying pallasites. But pallasites really come into their own when they've been cut into thin slices in the lab and prepared carefully so that the light shines through and they show the true beauty of outer space gemstones. I've had some of my most memorable and thrilling adventures in the world of meteorite hunting in search of these fascinating pallasites. Steve Arnold and I found several pallasites, each weighing in the hundreds of pounds. And that is quite an experience to pull a space rock out of the ground of that size and weight and know in your mind that about 50% of it is made up of gemstones from space. Now, mesosiderites and pallasites will both register very well on a metal detector because remember, they're about 50% metal. They'll also adhere very, very strongly to a good magnet. And while their compositions are different, they both tend to have somewhat similar features on the outside. You can see that these pieces, mesosiderite, pallasite, both exhibit some modest thumbprinting from surface melting. And some of these indentations that look like thumbprints are probably actually where crystals or other silicate materials have weathered out over time. Both of the stony iron subclasses tend to show a dark and somewhat rusty looking exterior. And if you look closely on the surface of pallasites, you can often spot the telltale glinting crystals that hint at the wonders hidden within. And it's worth noting that meteorites come in all sizes. Yes, I've found pallasites weighing over 200 pounds, and I've also found some weighing just a few grams. And this beautiful pallasite from Glorieta Mountain in New Mexico is a complete individual with thumbprints, fusion crusts, extraterrestrial gemstones. It's tiny, but it's got pretty much everything you could want from a meteorite. Not only are pallasites extremely beautiful and fascinating, but they're also super rare. And it's their formation story that explains their rarity. They're believed to have formed in the core mantle boundary of large asteroids. You'll remember me talking about how iron meteorites were once part of the molten core of a large asteroid. If you travel a little bit away from the center of the molten core, you reach this horizon called the core mantle boundary, where the molten material is beginning to cool and some silicate materials crystallize out. And that is where pallasites are believed to have formed. So out of the giant mass of a huge asteroid, it's only a little part that exhibits the conditions necessary for pallasite formation. And then that asteroid has to break up, perhaps by collision with another, and then that material has to make its Earth, and then it has to be found. Well, now that you're an expert in meteorite identification, maybe you're interested in going out meteorite hunting and trying to find some space rocks yourself. Or maybe you're just intrigued by the science and would like to start building a collection, or both. Whatever it might be, the most useful things that you can have for meteorite hunting and identification are a few representative samples. And here's a modest-sized stone meteorite, which I like to take in the field with me. And even though I've been doing this for decades, I always take what we call a throwdown specimen into the field with me. And the reasons for this are numerous. One is, you might just feel that you're more attuned to the cosmic identity of meteorites if you happen to have one in your backpack. But more realistically, your eyes and ears need to be retuned whenever you go out in the field. Meteorites have a very distinctive look when they're lying out in the desert or other environments, as you now know. So whenever I begin a hunt, I like to get a piece like this and throw it out into the landscape, maybe 20 or 30 feet away, just to see what it looks like, so that my eyes and brain are reminded of how meteorites appear in their natural and wild habitat. And at the same time, you can test out your detector, because different meteorites respond differently to different detectors. And so it's really good to know how your target rock sounds on your detector in that environment. At Aerolite headquarters, we sell a very useful item called the Meteorite Throwdown Package. It's very affordable, and it includes representative, handy samples of a stone meteorite and an iron meteorite. So every time you go out in the field, you'll be able to remind yourself what you're looking for. The knowledge needed for meteorite identification and meteorite hunting are different, but they overlap in many areas. And that's why I'm saving the real nuts and bolts about meteorite hunting for a future video. But I want to leave you with a few bits of information to see if these ideas spark your enthusiasm. And this is where we get serious, so the gloves are coming off now. You have gathered by now that I am quite a fan of the powerful rare earth magnet. But we don't just use them for meteorite identification, we use them in the field all the time for hunting as well. And here you'll see one of them attached to a very handy meteorite hunting device we call the magnet cane. And this was built at Aerolite headquarters. I never go meteorite hunting without one of these, because you really do not want to bend over 1,000 times a day to pick up rocks to discover they are not meteorites. So to discover how to build and use a magnet cane, please tune in to our next video. Ditto for this extraordinary device, which, believe it or not, is one of the finest metal detectors I have ever used. And it's folded down for travel. This is the Minelab SDC 2300. This thing is a meteorite finding monster. It's been all over the world with me, across the states, across the Sahara, found many meteorites and other fascinating things. And it's in its folded down travel state at the moment because it is one of the few detectors that fits into your handy backpack and goes right under your seat on the airplane. So this is an indispensable tool for the meteorite hunter. I absolutely love this unit. And we are authorized Minelab dealers. So if you have any questions about this detector or others, please don't hesitate to contact us and check out the specs of these amazing machines on our website. Some other useful items I always take in the field with me: a small digital scale for weighing finds, a lightweight but very powerful loop, which is powered by a battery, and you can use that to examine the extraordinary surface features of the meteorites we hope you're going to find in the near future. And of course, some bags to stow your finds in, and it's very useful to record the fine details using a marker on those. I feel that the best way to learn meteorite identification is visually, is by actually seeing the pieces and the characteristics that they exhibit. And if you want to be successful at finding meteorites, you really have to understand what meteorites look like, where they come from, and what they're made of. And I address those issues and many others in my award-winning book, How to Find Treasure from Space. This won an independent publishing award as one of the best science books of the year. And this is a revised and expanded new edition, over 150 pages, over 150 exclusive illustrations, photographs, diagrams. And I have put all of my accumulated knowledge, gained and in some cases invented over the past few decades, into this book. You can get it on Amazon, you can order it directly from Aerolite or from the publisher. I hope you now feel that you have a good grasp of the basics of meteorite identification. And I've given you a quick overview of some of the equipment that we use in the field while meteorite hunting, and you've met the definitive book to meteorite hunting, How to Find Treasure from Space. And yet, perhaps you crave more. And if you do, you will relate to the fact that the question I have been asked the most during the decades I've been doing this is, how can I go meteorite hunting with you? Before I actually answer the question, let me share an anecdote from Steve Arnold, my friend and hunting partner of many years, my co-star on Meteorite Men, and one of the greatest meteorite hunters of all time. Steve said, "There's no meteorite hunting aisle in your local megamart." And he is so right. And what he means by that is the knowledge required to identify and find meteorites is not something that you can pick up just anywhere. When Steve and I started doing this many years ago, there was no guidebook, there were no websites, there was no meteorite club. We had to invent the techniques and the strategies ourselves. And so who better really to share those strategies with you than us? Steve and I organize and lead actual meteorite hunting expeditions across the United States and around the world. We hold hands-on training camps where we teach you the nuts and bolts of using detectors, locating targets, recovering them, bagging them, logging your find locations, and we take enthusiasts on full-on adventures into the wilderness of the world. We've been across the Sahara, we've been to the Atacama Desert in Chile, and many other exotic and amazing locations. Some of our hunts have been incredibly successful, over 200 meteorites found on a single expedition. So if you'd like to join us on an unforgettable mission into the unknown in search of beautiful, rare, and fascinating space rocks, please visit meteoriteadventures.com and find out how you can go with us on a trip you will definitely never forget. I'll leave you with a final thought that has helped sustain me through the difficult parts of these expeditions, of which there have been many. And it is this: it's not us that makes the journey a great journey in search of meteorites. It's the meteorites themselves that make the journey. Every space rock that lands here on Earth has overcome almost inconceivable odds to fall upon our little blue-green Earth, which is a tiny target out there in the dark cosmos. And I've come to realize that every single meteorite find, no matter how small, still a treasure from space